Welcome to my talk, which is named An Engineer's Box of Chocolate. My name is Yves Glad. I'm from Germany, from Stuttgart. You can find us here in southern Germany. And usually we try to make things that fly around. We also do a bit of wind energy research, and one of our focuses is lightweight materials. For the agenda, I'll tell you a bit about life at the university as a research and development mechanical engineer. Then some points about Mathematica as an R&D tool, some short background info what I'm talking about, and then some short stories about, well, everyday use of Mathematica in not so glorious applications that save a lot of time, and the obvious conclusion. Now, life as a mechanical engineer, and probably you're familiar with the features here, and hello Oompa Loompas of science is sometimes pretty much summing it up. Sometimes we have to do things that are very hard to do, but are not very glorious, like the space toilet. But it's not all bad. Sometimes we get to do cutting-edge research, which just about means no one's got a clue how to do it, so you've got to figure it out. Thing here is surprises need not be pleasant. So sometimes things are really very hard, and customers usually don't see that problem, so it can be that difficult, right? So that's where the box of chocolates analogy comes in, because you never know what you're gonna get. Of course, there are things to be considered. Mathematica, to me, is kind of a, well, giant Swiss Army knife. I mean, this one really exists. You can buy it for some €100. Mathematica can be compared to that. It's got a lot of functionality, most of which you will never need to use, but still it's good to know it's there. If I were to be paid for selling Mathematica licenses, which I'm not, I'd say you can get things done very quickly if you know a bit how it works. So I'd say beginning is hard, but after a while you can get things done very quickly, and that's what is necessary. As an engineer, I'm not a mathematician or physician. I don't know, or physicist, sorry, I don't know. I don't need to know how everything works, so I just need to get the work done. And it should be okay in most of the cases. It's a tool which can do things for which no other tools have been developed. I think Theo Gray always puts it very succinctly. And it's got so much functionality that often you end up using stuff you didn't know existed like 1 hour ago, and I'll show you an example of that. It's got a really, really good help system, at least that's what I think. And the good thing is, if you work a while with Mathematica, the knowledge you gain is reusable. So it's not like with specific tools, very sharp tools, very narrow-banded tools, where you can become good at, but if it changes, then you've lost the knowledge. Mathematica is very universally applicable, and the knowledge you win can be used later on. We do lightweight construction, and a lot of lightweight construction is about how you use the material. It's not about the material, but how you use it. So you can take a piece of cardboard, and in this configuration, it's rather floppy. Say it has a flexural strength of 1, and if you take a clever configuration of this material, and put it like this, which is just plain cardboard, but very clever, then you get a really big advantage in the flexural strength without adding a lot of mass. So you get like 10 times the performance. So that's mainly what I try to do. We do new core materials for these sandwich applications, and one of these cores is just making the rounds. What I do is what I term modular isometric origami. So we fold a lot of paper, and I'll just give you a very short intro. If you're waiting for all the fancy origami stuff, you should have been here a year before. So today it's just bread and butter. But still. So essentially what you have here is just a large piece of paper. We apply a pattern. Let's look at this one here. We apply a pattern, and you see the red and the blue lines, and there are valley lines and mountain lines, and if you do that in a certain fashion, then you can just fold the structure isometrically without applying a lot of force, and you get this 3D structure which can be used for sandwich construction. Now this stuff is really new. And be warned, now we've left the sexy origami part, which is a lot of fun to do and for which Mathematica is a brilliant tool. So now we're entering the everyday realm of the university R&D engineer, which is me. So the code you're about to see may not be pretty. The code of my colleagues is worse still, but that's working code and we use it, and this really saves a lot of time. And I'm trying always to push the use of Mathematica here. So this is, well, in one of our labs, we use basically a large plotter to apply those lines, all right? And computing alone doesn't cut it. We need to produce the material. At least someone does. I'm getting paid for the computation, but still, we need to produce this stuff. And it can be hard work, and you see this poster here. That's some valued students who put that one up. I don't know what I said to them, but they have the feeling because this is Dima, Stefano, and Eva, three very trusted students who do a lot of work for me. They built this one, so it can be hard work. And if you consider all the stuff you need to do to produce these lines, it's not trivial, because with this, on this one job we have 130 meters of lines. And these need to be placed very precisely, like 0.1 millimeters within a certain area. And that's a lot of work, and I have about several thousand of these jobs, and they differ very slightly. So you have to do that quite precisely, and if you started drawing that in a CAD system, you'd just go crazy. And that's not even considering things like path optimization or, excuse me, machine optimizations and stuff. So this has to be automated. You cannot draw this on a one-by-one basis by hand. Well, at least not in Germany. It's too expensive there. I use a lot of homemade code, and I just wanted you to show these lines here. So what I needed was DXF code for a certain machine. And the Mathematica DXF export didn't work for me because it's 3D and it doesn't work with this certain machine. So I was experimenting with other software and it was quite horrible. So I had a look into the DXF specification and I wrote my own filter, although I'm really not a specialist on DXF. And well, it's not a lot of code. There's a lot of replacements going on, but it's about like 30, 50 lines of code, and you have a perfectly functioning DXF export. And I wrote this, I don't know, 5 years ago, and it works without a hitch. So it's very, very easy using replace and other functionality. Then, once we've produced the samples, it's rather sad. We need to destroy them in the process. So we glue them between the two face sheets, and this is a compression test. So we put them in a rather massive setup here. And we crush it quite to the death, which is important because you need to know how much the material can stand. Now we have a lot of these samples. You can't read the numbers on this one, but we have several thousand of these samples prepared. And of course, what we get is XY data of the displacement and the force needed for this displacement. And one thing is, there are no existing tools to extract the data that we want. For example, the compression modulus, because the material is non-standard and there are no valid test norms. So one way to do it is to import this text, this data into Excel and go bug crazy because it's horrible to extract data. Well, to work with Excel in general, I'm sorry, but to extract certain things and to do statistics like smoothing and so on, so this is not feasible. So after a lot of pain from my colleagues, I decided to help them and write a more comprehensive package which does nothing else than just read in the data, and there's a bit of heuristics involved, so we have an auto detection, which machine was used, which sensors are relevant, which units are put into these measurements, and so on. And then you can just read in the data. Plotting is, of course, trivial. I put my own legends in here because the existing legends are not very comprehensive. And this is in fact a working notebook from my colleague who does all the measurements. I just did the notebooks. So I showed him just what you can do and like tab views and stuff. So that's quite nice. And you can look at all the things. I mean, this is, until now, it's not very exciting. The exciting stuff is that you simply define, it's modular. You simply define the method you want to subject the data to, and then you decide which measurements you want to be taken, and so on, which smoothing algorithms, etc. Of course, there are default options for that. But what you do is essentially you define a script which tells the package what to do with the data, and that can be automated. And another thing with this package was we needed a connection to a, well, in that case, Access database where we save all the measurements. So we need the dimensions of the samples, we need their weight, and so on. And this is more convenient to store in a database. So it pulls in the textual data from the measurements and correlates that with the data from the database, pulls them in, and if these fields are with a green background, then it says, okay, a check has been performed and the data is valid and we have this data, otherwise it would be red. Which is quite important because if the students forget to input the measurements, then you're in a world of trouble because all the evaluation crashes. Okay, I see. So this is too big. So this is what you get. So we've performed the evaluation, and what you have here is the tension and the displacement of the probes, and it's also normalized to 0, and you have different slopes for the modulus, and this interface was written by a colleague of mine, so you can see that there's a curly braces right here because he didn't take care of the braces, but it works anyway, so this is pro. And he wrote this interface as well where you can just choose what to look at, which kind of modulus you want to take a look at, and all the data is also displayed in the legend, so you can't go wrong with this package, more or less. So this is quite, well, sounds quite trivial, but it saves a lot of time because we're not yet sure how to evaluate all those values in the end. And if the customer says, no, I want it that way, we can just evaluate all of the data with one script, and that will save like tons of time. Yes, and there's the always, I don't know, bugging difference between model and reality. So Mathematica generates beautiful 3D data, and my folding algorithms line them up perfectly, so it's really nice to look at. But if you produce stuff, things, well, things do not go wrong, but things are as they are. You have the thickness of the material, you have imperfections, somebody's got a bad breakfast or a bad day, so these samples are not uniform. And this influenced the measurements, so we had quite a difference between the prognosed properties of the material and the actual properties. So we knew, okay, let's have a look into that. And that's another example. I used Mathematica for surface reconstruction. We have a rather expensive, fancy stereoscopic camera setup where you can scan, well, small parts with very nice accuracy. But what you get back is a rather dirty STL set of data. So this is the data you get from the scan. The resolution is good, but it cannot, well, it's not always perfect. You see these ragged holes and stuff. These are just artifacts from the scan process. And you cannot put this thing into an FEM model. It will not be very nice. So what I did is I did a bit of post-processing of the data as a listplot 3D, and then I extracted the cross-sections. As you can see, it's, well, this was one-off. It's not, I just did it once. It's not packaged or something. Then we identify certain important points here, and then we cut the unit cell off at these points, and we try to check if it's still valid. That's good. And then there's some kind of B-spline thing to get a nice domain to interpolate over. If we use that, we get a fairly nice representation of the model, and it's already more finely spaced at the edges, where it's usually more important for FEM programs or FE programs to get a nice solution. So this is all scripted, automated, quite fancy. And with this, well, after this final reality check, you can export this data directly into, here you are. So this fits quite nicely, and we've got rid of the holes and stuff. And you can export this with a little bit of knowledge how the formats look like into, this was Nastran code, and my colleague is able to run the FEM simulation directly from this point. And that would be quite difficult with other tools, and yeah, it might be the way to go for further testing. The honeycombs are also a good sandwich core material, but these are also not produced in a perfect fashion. So there are imperfections, and the cells are not really all perfectly shaped. And my colleague wanted to know, okay, so how do they look like? Because they always tell us, oh, the honeycombs are so good, and well, they're not perfect either. So he had this brilliant idea just to take a sample and scan it. And then this one is really ridiculous. So we scanned it, all right, we imported a PDF that works just fine. You can see that. Well, I took a smaller part of the image without the fingers and stuff to analyze it. I did a binarize. That's just, well, it's not very complicated. And then, this is the ridiculous part, I just applied morphological graph. And this is ridiculously powerful. And I was going, hey, in the office, because it just worked on the first try. And then what you have to do is extract the vertex coordinates, which is a bit of a hack, but you can get this graphics object, and then you just extrude and scale the whole thing. And well, I was lucky because I remembered a talk from Marcus and Shady last year, which showed something like this, and today there was also just a very similar example. But I went into my colleague's office and said, okay, is that what you want? And he was just, well, yeah, he couldn't answer. He thought I was pretty good at what I did. But that was just, well, coincidence. So you need not be very good. And I don't have a clue about morphological graph thingies, but well, it's easy to do, right? You just got to remember someone who did it. Then dimensions, well, computing is easy for me, but then I have to explain to the other guys, okay, how is it done, and so on. And, well, I did a bit of, well, fancy formatting, so this is not in 2D, this is, in fact, this is in 3D, and it's quite nice to show in which planes the measurements are taken, and so on, and engineers like that. But it's also quite hard to do in Mathematica, because getting the characters after version, well, starting with version 8 is quite the works. But still, these graphics tend to live a very long time. Everyone reuses them, so it's worth the effort to do it properly. Then we have a bit of fancy origami. I'm not going into that, but it's about scripted visualization. So the stuff I do is very visual. I have to show people images, and I have to test how does it work, and so on. And I've got such a lot of these items that I need to define functions dealing with this stuff and formatting them, and this has to be scripted. And you can get a very exclusive preview of some of the images in my thesis. So this is just eye candy, but it's all done with Mathematica, and there's not, those are all scripted. There's not one step that's done by hand. So I can rerun these and change things very quickly. And that's the only way to deal with about, I don't know, it's about 100 nice images, I think so. You can see a lot of use of grid and stuff and colors and things. Also some, well, use of real images and so on. Again, a bit of graphing, well, a bit of everything actually. So, well, with a bias on yellow, I know, but still we have a graph of all the geometries we use in our production and so on. So I use Mathematica quite intensively. Here we are, and so on. So this is something you can probably only manage if you, well, take out all the steps you usually have to do by hand. I mean, Michael did a book with many more graphics. He should know. Then we are nearing the end, and I do have a final quiz, and there may be a prize. So anyone who can tell me, let's have a look. So we're getting back to the fancy stuff. So we've left the everyday usual area. I have 2 stripes of paper. They are colored, and what you can see here are the creases, and that's the crease pattern. And if anyone can tell me what one of these stripes is gonna become, then he'll keep these. So which one? Yeah, you can pick one. Okay. No one else? So I'll start with this one. Huh?
Propeller blade.
Propeller blade. You're crediting me with far too much competence. No, this is really quite. Yeah, it might be some kind of strange screw, but in reality, it's kind of a apple-shaped torus knot. It's a knot. It's some kind of knot. I just use knot data and use that to do a bit of paper folding around that. So this should keep you well awake at night, but it's foldable. It's foldable. I just haven't tried it. The other one, and this one I actually folded. I can show you the pictures. So this one I showed already last year. So it's all very symmetrical, and in between you get kind of a para jumper here, but then it becomes more elaborate, and in effect becomes it's a pseudo fractal structure which uses a piano Hilbert curve as skeleton. What you saw is the exact animation of how the kinematics would work if they didn't intersect each other all the time. So this is not what you can do in reality. In reality, you have to bend the stuff, but this is pure mathematics and very impressive. And so this is what I do if my colleagues don't bug me about certain packages. So as a conclusion, Mathematica is pretty good. That was done with Mathematica, by the way, so I do the image processing as well. It's very versatile. Can be used in many surprising way. Well, even if you're totally incompetent and don't know what you're doing, if the result is good, then there's a high chance it might work again. So that's quite well, and you can it really can help make your life easier if you have tasks that are really like repetitive or time intensive. And then there's a certain thing you can really impress your colleagues. So I'm always happy to help them out with a line or so, and they are always very impressed. Thank you for your time, and if you have questions, I think it's coffee break anyway. Thank you.